Now this is an example of how this was applied in construction materials research. So the idea was here to determine how much of the superplasticizer that you add to a cementitious system in the beginning stays on with respect to time. So we know that one of the primary means of or mechanisms of action of a superplasticizer is to adsorb on the surfaces of the cement particles. Okay. Now if all the superplasticizer that you add into the concrete gets adsorbed on the cement particle surface in the beginning itself, then there will be a rapid drop in the tendency of the superplasticizer to disperse the particles. So what we want ideally is a system where some portion gets adsorbed in the beginning, while a part of the superplasticizer remains in the solution and gets adsorbed at later stages. So here we wanted to find out, based on the chemical species of the superplasticizer, what was the tendency of these superplasticizer molecules to get adsorbed in the beginning or with respect to time, or how much superplasticizer was still remaining in the solution. Now the problem here is we need to extract the superplasticizer from the cementitious paste. Okay, so one way of extraction is by ultra centrifuging. Okay, we do ultra centrifuging. What is the principle of centrifuging? You rotate at very high speeds so that you can separate the solid and liquid phases. So right after cement paste is mixed with the superplasticizer and the water, right, you do this ultra centrifuging to remove the solution, which will essentially contain water mixed with your superplasticizer. So you repeat this experiment after 1 hour of mixing water and superplasticizer into the cement. The solution that you separate will have water and some part of the SP which did not get adsorbed onto the cement. So that is what essentially was being done in this case, and you can see here the absorbance spectra, UV absorbance spectra for the different chemical species. In this case there were 4 different chemical species that were used. One was lignosulfonate, one was sulfonated naphthalene formaldehyde, one was sulfonated melamine formaldehyde, and the final one was polycarboxylic ether. So these are 4 different chemical families of superplasticizers, and you can see for the plain molecules, for the plain superplasticizers, the absorbance spectra are quite different. For instance, for lignosulfonates, the primary absorbance happens at a wavelength of 205 nanometer. So where is that? Is that in the visible range or ultraviolet range? It is in ultraviolet range. In fact, all of these 4 compounds are in the ultraviolet range, but they have very specific wavelengths at which absorption actually happens. So if you are taking the solution which is removed by ultracentrifuging and subjecting it to ultraviolet visible light spectroscopy, you can detect the presence of these species, and by calculating the relative heights of the absorbance spectra, you can determine how much of it is actually remaining in solution from one time to the next. Okay. So while this result is not entirely 100% accurate, but what it's tending to show you is that there is a good correlation between loss in fluidity and adsorption of superplasticizer. The greater the tendency of the superplasticizer get absorbed on the cement particles in the beginning itself, the faster is the loss in fluidity. So what we generally come to notice in this case is that the systems which have polycarboxylic ether in them tend to have a larger amount of the superplasticizer remaining in solution even after 90 minutes of the mixing of cement and water. So that simply tells you that the greater effectiveness as far as dispersion is concerned would be obtained from these kinds of molecules. So I would not completely expect this result to be 100% correct, because again look at the extent of dilution that was necessary in several cases, because the amount of solution that you collect even after centrifuging is going to be only minimal. So in this case the solution was diluted 1000 times. Okay, so you need to ensure that you are reading your data correctly with respect to the kind of solution that you have extracted. So if you get only 1 milliliter, if you want to have a substantial amount ready for your analysis, you need to dilute that to 1000 milliliters in this case. Okay. Right, so I did not spend that long on ultraviolet visible light spectroscopy because you are operating nearly in the same range as you do for atomic absorption or emission spectroscopy. However, when we want to look at organics present in the system, or when we want to look at the types of bonding for the compounds that are present in the system, we move on to a different range of spectroscopies based on infrared. So, infrared obviously has a wavelength that is higher than visible light, because of which its tendency to induce electronic transitions becomes lower and lower. At the extent of energy that infrared radiation has, you can only excite vibrations in molecules. So, essentially infrared spectroscopy deals with measurement of wavelength and intensity of absorption of mid infrared light by a sample. So, we have 3 regions in infrared. You have near infrared, mid infrared and far infrared. So, in this case we are talking about mid infrared region, which is essentially 2.5 to 50 micrometers of wavelength. And very often, as far as infrared spectroscopy is concerned, the wavelength is referred to by wave number. Now, what is wave number? It is nothing but one over wavelength. It is just 1 over the wavelength, okay, where wavelength is in. So, 4000 corresponds to 2.5. So, wavelength is in micrometer. So, wavelength has to be expressed in millimeter in this case. So, if you have 2.5 micrometer, so 1 over 2.5 into 10 power minus 3 millimeter, right, that is equal to 400 millimeter inverse, nothing but 4000 centimeter inverse. Okay. So, wave number is nothing over but just another representation of 1 over wavelength. Why is this sort of representation chosen? Because energy is proportional to 1 over wavelength, right. So, energy in this case is proportional to the wave number. Okay. Now, there are several types of molecules that your system may have. Some of these are molecules that are not going to be active as far as infrared is concerned. What do you mean by that? If you have homonuclear diatomic molecules like oxygen, hydrogen, nitrogen or chloride or chlorine, these will have no response to the radiation because they are going to be inactive as far as infrared is concerned. Now, when you consider a system to be inactive, interaction only happens when dipole moment of the molecule changes with vibration. Okay. Only polar bonds are infrared active, and the stronger the polarity in the system, the stronger will be the infrared spectrum that is produced by these materials. Okay. Polar means what? What do you mean by polar? When there is a separation of charges happening between the elements that make up the molecule. Okay. Can you give me examples of other polar compounds? What about water? Is it polar or non-polar? Water is polar, right. There is a separation of charges that happens at the bond, and that the stronger the difference in polarity, the higher will be the absorption spectrum produced in infrared. Okay. So, in this case of homonuclear diatomic molecules like oxygen and nitrogen, you have almost neutrality as far as charge is concerned, but here there is a charge imbalance because of the relative sizes of your hydrogen and chlorine atoms inside the HCl compound, right. So, there is a charge imbalance that leads to polarity, and this polar system will definitely be infrared active. So, the range of infrared we are talking about from 2.5 to about 50 micrometers. So, this is the mid infrared system. Of course, here only 25 is marked, but 2.5 to 50 would be the mid infrared region. Beyond that becomes your far infrared. Less than 2.5 micrometer is near infrared, that means which is closer to visible light. Okay. So, what happens as a result of absorption of this infrared radiation is that polar molecules tend to start vibrating because of the different types of vibrations that may actually happen in the molecule. So, since there is a charge imbalance, when you supply radiation to it, there are different kinds of things that may happen. The bond may start extending, or it may start bending or rotating. So, a lot of different things can happen to the bond because of this absorption of the radiation. So, IR spectroscopy simply exploits the facts that molecules have very specific frequencies at which they can rotate or vibrate corresponding to discrete energy levels. Once again, any transition that happens either in an electronic system or a molecular system happens at very discrete energy levels. So, for example, if you have a hydrogen and chloride bond and you are talking about the specific energy that will excite the stretching of this bond, there will be only one single value for that energy that creates this stretching. If you are talking about the water molecule with a 2 hydrogen and 1 oxygen atom, right. So, you have the oxygen at the center and the hydrogen attached to it. So, there can be stretching of the hydrogen atoms, there can be bending of the bond and so on, but each one will happen only at a specific energy, because energy levels are always discrete as far as atomic structure is concerned. So, what you are simply doing is looking at what specific frequencies does this particular transition occur. In this case transition, I mean vibration occur, okay, and then you can relate that to the specific elemental species that are present in your system. So, the frequency of the vibrations can be associated with a particular bond type. Infrared is collected of course by passing infrared light through the sample, and how much of the energy gets absorbed or transmitted can give you an indication of specific wavelengths at which you can induce vibrations happening in the system. Now, we have seen several systems, we saw that you need to actually isolate the wavelengths to send them through the sample, or you can have, in the case of UV visible spectrometers, we talked about the array detectors, in which case you can collect all the wavelengths together at the same time. Similarly, in the case of Fourier transform, to make the technique a lot more robust, okay, either we can use a monochromatic beam which changes its wavelength over time, that means you disperse the wavelength to very specific ranges, or you can collect all the wavelengths together and do a Fourier transform, right, to measure all the wavelengths at once. So, that is why today what we typically call IR spectroscopy is FTIR spectroscopy, Fourier transform infrared spectroscopy. The idea is that you can isolate all the frequencies or all the wavelengths at once, rather than having to individually choose wavelengths of infrared light to be passed through the sample. So, the spectrum here is quite similar to what you had in the case of absorption spectrum seen previously, okay. So, you plot the absorbance or the transmittance of the y axis and the wavelength on the x axis, but in this case we do not plot the wavelength, we plot the wave number. So, we plot the wave number on the x axis and the percentage absorbance or percentage transmittance. Once again, at specific wave numbers we will be generating certain peaks, and that will be indicative of the species that are present inside the system. So, this is just an example of the different types of vibrations that can actually happen. So, considering the CO2 molecule, which is nothing but a linear molecule, right, because there is no angle in the bonds between carbon and oxygen. So, in this case if you have a symmetric stretching, that means both sides are stretching equally, right, that means you do not really get a charge imbalance in this case, okay. So, because of that this sort of a system will be infrared inactive. On the other hand, if there is asymmetric stretching, right, that will be corresponding to a specific energy absorption of infrared light, and that happens specifically at 2349 centimeter inverse wave number. Deformation vibrations which lead to a change in the linearity of the structure can happen at 667 centimeter inverse. So, is the energy higher or lower here? Where is the energy higher, in the asymmetric vibration or in the deformation vibration? So, the higher the wave number, the higher the energy. So, in the case of asymmetric stretching vibration, you get a, that happens at higher energy levels as opposed to deformation vibrations which are possible at lower energy levels. Now, if you consider a nonlinear molecule like water H2O, So, here you can have symmetric stretching vibrations where the oxygen goes this way and the hydrogen go in the other in their specific direction. But even in this case you would get, I mean this will also be infrared active because this would, there is no balance in this case also. So, because of that this specific stretching vibration actually happens at around 3600 centimeter inverse wave number. Asymmetric stretching vibration happens when you get differences in the way that these bonds are stretching. Now, for ease of understanding, just imagine that these bonds are springs, right. So, what happens when you stretch the spring or when you compress a spring? When you stretch two springs together at the same time equally, or when you stretch one spring with one force, another spring with a different force, and so on. So, that creates your stretching which is either symmetric or asymmetric. Deformation vibration happens when you are change in the structure of the material, and again in this case these are possible at lower wave numbers like 1595 centimeter inverse. So, just to give another example from the structure of acetaldehyde. So, here of course we have different types of bonds. You have carbon hydrogen bond, you have carbon carbon bond, and carbon oxygen double bond. Okay. Each of these will have specific vibrations associated with the stretching or deformation of these bonds. Okay. So, here for instance the carbon hydrogen stretching can happen. Okay. Here again the bonds are represented by springs. So, stretching simply means extension of the spring. The CH3 itself can deform as a single unit. The carbon hydrogen can deform, okay. The relative angle between carbon and hydrogen with respect to the horizontal axis may get changed. The carbon oxygen double bond may also stretch. Okay. So, for each of these transitions you will actually get a specific absorption of the IR in your absorbance spectra, right. So, with this what we are trying to do is deciphering the structure of the molecules that we are interested in. Now, in the case of cementitious materials, what would you expect to see? What kind of bonds are there in cementitious materials? No, what sort of bonds? Between what elements? You have SiO, then aluminum oxygen, right. You may get carbon and oxygen from carbonate species that are present in the system, right. Then you have OH, oxygen and hydrogen, and so on. So, for each of these specific bonding systems you will get a signature as far as your FTIR spectroscopy is concerned. So, the typical IR absorption wavelengths are divided into two groups. One is called the fingerprint region, the other is called the functional group region. At the higher end of the absorption spectra, that means at higher wave numbers, what you get are called functional group regions. So, here nitrogen hydrogen group, alcohol group OH and so on, these are essentially the functional groups that may be present in your systems. On the other hand, when you go towards the lower end of the wave number, what you get are the fingerprint, which essentially corresponds to the presence of single bond or double bond or triple bonded systems. Okay. Based on the specific sets of wave numbers at which you get these transitions, you can then approximately estimate the composition of your structure of the material. Now, again you will obviously need to compare with the database to try and understand what each peak signifies, For most of the standard bonding systems like carbon carbon triple bond or carbon carbon double bond, there are very specific locations at which transitions happen like stretching or bending and so on, and you can associate that with the peaks that you observe for your sample and then figure out what actually is present in your sample. Okay, we will see some examples in just a minute. So, these are the different regions, as I said. In the infrared spectroscopy you have the functional group region on the left and the fingerprint region on the right. So, this is an example of spectra. This is the polyethylene spectra on the top and polystyrene at the bottom. What is the essential difference between polyethylene and polystyrene? Polyethylene and polystyrene, the primary difference is polyethylene is aliphatic and polystyrene is aromatic. So, you will have benzene rings in polystyrene, right. In polyethylene you have carbon hydrogen stretching vibration, which is being measured at close to 3000 wave number, you have the methylene scissoring vibration and rolling vibration. Okay. Whereas in styrene you will have to somehow differentiate the effect here. The stretching of vibration between carbon and hydrogen happens inside the benzene ring in this case. Okay. So, because of that your specific frequencies or wave numbers at which these kinds of transitions happen are going to be quite different from the carbon hydrogen stretching which happens in the case of polyethylene. Okay. You can also get skeletal vibration of benzene rings, the complete vibration of the rings itself, that can produce such kind of IR spectra. Okay. And you can also get out of plane deformation vibration of carbon hydrogen bonds which are recorded later. But you can see the spectra becomes a lot more complex for structures like benzene, whereas for simple aliphatic structures like polyethylene you get very specific peaks that mark the presence of certain types of compounds. So, just a little bit more information on the technique itself, just to try and understand how are these spectra produced and what does Fourier transform actually do in the system. So, again you have the light source. Okay. This light then passes through an instrument called the interferometer. The interferometer essentially brings out light rays that are either completely in phase or out of phase based on the movement of some mirrors which are inside the interferometer. I will just come to that in just a minute. And this light that comes out of the interferometer then passes through your sample and creates what is known as an interferogram, and this interferogram is then subjected to what is called the Fourier transform process. Now, Fourier transform is something you have learnt in mathematics, but we will again just go through what is going on here. So, once again we have a background presence in the sample, right. We are operating at infrared wavelengths. So, there is sufficient amount of infrared radiation in the background also which needs to be removed from the system to actually get a clear understanding of the absorbance spectra for the sample itself. Okay. And ultimately we get what is known as the transmission spectrum. So, here the percentage transmittance is plotted against the wave number on the x axis. Okay. So, how do we actually generate this light that passes through the interferometer? So, these are old IR spectrometers which were quite similar to the layout that we saw earlier for the ultraviolet visible light spectrometers. So, here the infrared source radiation is actually sent separately through the reference and through the sample, and then you basically send it through a monochromator to isolate specific wavelengths and detect the specific wavelengths at which absorption has happened. Okay. Now, the problem here is it is a very cumbersome technique, because for every wavelength you will need to actually adjust your diffraction grating to ensure that you are actually able to capture that wavelength. A more robust and sophisticated technique is actually to capture everything at once and determine by Fourier transforming the signal as to what are the frequency component present inside your light, and that is what we are talking about with the new IR spectrometers. So, what is happening in this case? So, this sort of a interferometer is also called a Michelson interferometer, and this is something that you have learned before in physics in school, but I am sure that you would have forgotten this. It would be a good idea to actually look at Michelson interferometer designs on the internet. You get very good information from Wikipedia itself about this. So, what happens in this interferometer is that you have a fixed mirror and you have a moving mirror. So, light is going from this light source onto a beam splitter that sends the direct beam to the fixed mirror and a reflected beam to the moving mirror. So, what will happen at a specific location is that the light beam that is coming through the fixed mirror towards the sample and from the moving mirror towards the sample will be completely in phase. Okay. But at certain lengths of the moving mirror there will be some out of phase as far as the two beams are concerned. Okay. Now, as a result of this you will produce light which comes out from this beam splitter going towards the sample, which has some constructive and some destructive sort of wave nature. Okay. So, here to obtain the absorption spectrum, one mirror moves by fixed distances to generate interference in the radiation reaching the detector. Okay. Okay. So, what you are simply doing is instead of sending the beam directly through the sample, you are causing it to have components that have constructive or destructive interference while you send it through the specific sample. The absorption spectrum is a function of the wave number obtained from Fourier transform of the interferogram, which is a function of the mirror movement. So, if you can compute the distance over which the mirror is moving, you will actually generate specific wavelengths at which there is constructive interference which go right through the detector. Oh, sorry, not through the detector, through the sample. Okay, only at certain lengths of the moving mirror you will produce a constructive interference. And because this function of the mirror movement can be captured as the specific wavelengths over which absorption occurs, then you can actually generate what is known as the interferogram. So, again I think we are out of time, there is a lot more information that I wanted to give you here. So, let us continue this in tomorrow's class.